Hello, and welcome back to a video series on MAT 1033 Intermediate Algebra. This is video number 45 in the series, The Quadratic Equation. My name's Sean Perry. So we will now introduce a powerful tool in the study of quadratic trinomials. In later classes, you may actually get to see how this is going to illuminate lots of things about polynomials, even polynomials of higher degree. For now, I'll just mention that this is an exception to my, hey, you shouldn't memorize things guideline. Really, the guideline isn't don't memorize stuff. Obviously, you have to memorize things in mathematics. Really, you want to make sure that you're only memorizing the central or really useful or really tricky to derive stuff. And this one happens to be all three of these things. So here's your critical notes. Copy this down, memorize it, tattoo it on your arm, whatever you like. This is going to be the quadratic equation. If we have a quadratic trinomial ax squared plus bx plus c equals 0, then our x's are given by this formula. Negative b plus and minus the square root of b squared minus 4ac over 2a. It's a mouthful. Take the time to memorize this equation. This formula is a big, heavy weapon. This is our bazooka for solving quadratic trinomial equations, but it always works. If factoring is possible, though, you should do that. If you can factor the trinomial, it's faster, you should do it that way. If you can see a special product formula for it, you should do that too. But if the answer to this equation is irrational or complex valued, you're not going to be able to factor this over the integers. And so you're going to wind up needing this equation in order to get the answers. By the way, this formula works even if the coefficients are complex numbers. We're looking at real polynomials. Specifically, we're looking at integer polynomials, whole number polynomial coefficients. But this formula works even if they're not, even if they're radicals, even if they're complex numbers, the quadratic equation holds. Let's see how we would use it with an example. Here I have x squared plus 5x minus 6 equals 0. This is a good one to start with because this one actually does factor, so we should make sure that, it produces the same results. Our a term is a 1, our b term is a 5, and our c is a minus 6. We need to keep track of signs for this formula to work. We plug all those into the quadratic equation. That looks like this. And we evaluate it using order of operations. There's an implied parenthesis around this whole thing under the radical. You need to do that part first. So let's start inside that. There's an exponent. Take care of that. That's 25 for 5 squared. Then we could take care of this minus 4 times minus 6, which gives us positive 24. We combine those two to get 49. The square root of 49 is 7. And so we have negative 5 plus and minus 7 over 2. Now, I would split that at this point into two separate equations, right? You have one for the positive plus 7 and one for the negative minus 7. Negative 5 plus 7 is 2, so we wind up with 2 over 2, which is 1. And for this one, we have minus 5 minus 7 is minus 12, divided by 2 is minus 6. And of course, we could have done that by factoring. This is just to check our work, or just to get us, used to the idea in a way that we can verify. What would that have looked like factoring? It would have looked like this, right? We would split it up into parentheses, then we figure out what goes in those parentheses, and then we use the zero product property to split them into two equations and solve each linear equation separately, giving me the exact same answers though. But we can now even take on finding the zeros of prime polynomials. That's the real advantage of the quadratic equation. Here's a prime polynomial. We identify the coefficients, a, b, and c. That's 1, negative 2, and 3. We plug them into this equation. That looks like this. We evaluate this inside part first. This is going to give us 4, and this term is going to be 12. We take that difference, we get minus 8. Well, the square root of minus 8 is 2i radical 2, if we simplify it. So we could split this into a positive and a negative case, and then we could divide the 2 into each term, or factor out a 2 and cancel it, to give us 1 plus radical 2i and 1 minus radical 2i. We'll always be looking for a number and its conjugate in the complex case. Now, part of the quadratic equation in particular is worth some special attention. That's this inside part of the radical. The radical is the really complicated thing that's happening here, and it's going to make our irrational numbers pop out. If there's irrational numbers that are going to pop out, it's going to make complex numbers pop out if that's going to happen. So we should take a look in a more detailed fashion at b squared minus 4ac. Actually, we look at it often enough that it gets its own name. This is called the discriminant. It discriminates between different solutions. It's going to determine whether or not we're going to have rationals, whether or not we're going to have irrationals, or whether or not we're going to have complex numbers in our answer. It's also going to determine how many answers we have. It'll tell us whether or not there's going to be two answers to this equation, or if there's just going to be one answer to the equation. So here's some critical notes. I want you to copy this down. These are some facts about that discriminant. These are properties of the discriminant, you could call this. So the discriminant of ax squared plus bx plus c is b squared minus 4ac. If this is positive, you're going to have two real numbers as your roots. If it's 0, then you'll have plus and minus 0. That's only going to give you one rational number for your roots. And if it's negative, you're going to get two complex roots, because then you'll have a negative sign under the radical, which will give you an I. Now, if it's greater than 0 and you're in the real case, and you don't get the square of some rational number, so you don't get, like, I don't know, 9 or 25 or 9/4, something which is actually a square of a rational, then the radical will be irrational, and you're not going to be able to simplify it. You're going to wind up with a radical in your answer. So the discriminant tells us a lot. Let's look at an example of that last one. Actually, we already did see an example of this, but let's look at another example just to drill it home. What if I had a polynomial? Here I've written it in function notation. Don't worry about it. What if I had a polynomial given by x squared minus 4x plus 1? Well, what are its zeros? When is p of x equal to 0? We could find that using the quadratic equation. Here I have a equals 1, b is minus 4, and c is 1. So plugging this in to the discriminant, we have 16 from negative 4 squared, and then minus 4 times 1 times 1. That's minus 4. This is a 12. Now, because radical 12 doesn't reduce, we know that's 2 radical 3. This means that this polynomial doesn't have any rational roots, and that actually means that it's not going to factor. So you could look at the discriminant really quickly to see whether or not something factors at all if you know a little bit about your squares. Let's briefly talk about the relationship between roots and factors. This is something that will be much more important as you proceed through your later math classes, especially the next one, college algebra, but I'll just offer it right now as an important fact. So here's some critical notes. Copy this down, show it to me later. If x minus b is a factor of a polynomial p of x, meaning you could write p of x as another polynomial times x minus b, then if you plug in b, you're going to get 0. And that's because this term here will be 0 if you plug in b. B minus b is 0. And then 0 times something, if it's a factor, you're timesing by it, will give you 0. So we have this relationship between factors and zeros, as you've probably guessed by solving some of these equations. Now you could see it real quick, right? If we write p of x as x minus b times some q of x, where q of x is any other polynomial, and I plug in b here, I get 0 times that polynomial. Boom, p of b is 0. So actually there's a stronger statement we can make, right? Because this is really an if and only if statement if we're talking about factoring over the right stuff. Right? If b is a whole number, for example, and we're factoring over the integers, then we could write this x minus b as a factor. If b was the square root of 2, x minus the square root of 2, we don't consider that to be a polynomial over the integers. So there's a question about factoring out here that's kind of subtle. So I won't make the if and only if claim yet, but I will say if we are factoring over the appropriate set of coefficients, then there is an if and only a statement. You only have zeros who correspond to factors. We'll see, again, in the next class in college algebra, we'll explore that much more deeply. In the meantime, what's this mean? What can I do with this? It means that a quadratic equation is going to give you a whole number or a fraction if and only if you could actually factor the polynomial. So the quadratic equation somewhat tells us if we could factor or not. Let's take a look at the example 3x squared plus x minus 4. If I have my coefficients set up this way, they're 3, 1, and negative 4 respectively for a, b, and c. I plug them in, and what do I get from my quadratic equation? I'm going to get two fractions. I'm going to get 1 and negative 4/3. Okay, so those are two fractions. That means this original polynomial could factor. Let's see that, right? That means that these might be factors. I mean, here you can kind of see how this looks a little odd, right? This isn't an integer like we're used to. Actually, what we can do is rewrite this x plus 4/3 term so that it gives us an equivalent term with only whole number coefficients. Let's see what I mean. What we could do is set it equal to 0 and find an equivalent term that has whole number coefficients. Take x plus 4 over 3 equals 0, multiply on both sides by 3, and we wind up with 3x plus 4 equals 0, a new term which has the same 0 at negative 4/3. And this is actually going to be the term we want. We could factor the original polynomial using these roots found from the quadratic equation in this way. But I do stand by the fact that it's much faster to factor this using the AC method. We're just looking at this to see that the quadratic equation syncs up nicely with what we've already learned about factoring and the zeros of polynomials. Okay, time for some praxis. I want you to do some practical exercises. Pause the video at this time and give each one of these a shot. Remember, you're going to need to set things up appropriately before you begin. Then use the quadratic equation to solve. Okay? Let's see how you did. With the first one, we're already set up pretty nicely. We're already set equal to 0, so we can already kind of pick out our factors here. If I have a is 1, b is 3, and c is 1, and we plug that into the quadratic equation, it looks like this. Remember your negative sign in front of the b. That's a common mistake. Now, we simplify the discriminant first, and we have an irreducible square root. So we really can't go much farther than this, although we oftentimes will split this up into two fractions. That's pretty normal. I will take either answer, they're equivalent. This one's not set up yet. You need it to be ax squared plus bx plus c equals 0 before you begin, and the easiest way to do that is just moving this quadratic term over to the other side. Then we have the following a, b, and c. We plug that into the quadratic equation, evaluate the discriminant first. We wind up with negative 11 here. That doesn't reduce. In fact, it pulls an I out in addition to having a square root of 11. And splitting up the fractions into two parts, we get the following 2. This is one of the reasons we do split the fractions up this way, is because now I can write it as a plus bi and a minus bi, a number and its conjugate. For any real polynomial, if you have a complex answer, you'll always have its conjugate as another answer to the equation. All right, so here I have some supplementary notes. The main video is done, but maybe you want to know where this came from. I mean, it seems like the quadratic equation just comes from on high, but actually it doesn't. It just comes from completing the square. So we learned in the last video, in the final part of the video, about what is completing the square and how does it work. And what we're going to do now is we're going to derive the quadratic equation. So what we do is we start with the general trinomial, ax squared plus bx plus c equals 0. Now let's move the c over to the other side. We minus c to the right-hand side here. Then we focus on the middle term. Completing the square says take half of this middle term, square it, and add it to both sides. But before we do that, let's get rid of this a term, because we looked at things that look like x squared plus something x. We didn't look at the a term, right, in the completing the square methodology. So let's divide by a, and we wind up now with something that's just a polynomial. X squared plus b over a x is equal to minus c over a. Notice we had to do it to both sides. Okay, now let's get into completing the square. So this is going to look a little bit weird, but it's still just half the middle term, b over a divided by 2 is b over 2a, and then squared is b squared over 4a squared. So I want to add that term to both sides. Now, why would I want to add that term to both sides? Now you can see that we've managed to get this term, this right-hand side has become much nicer. It's now a perfect square, and so we've isolated the square. And the expense of that was having a b squared over 4a squared on the other side as well. No big deal, actually, but it's still a little messy here. We maybe want to do this fraction subtraction. So if I'm going to do the fraction subtraction here, I need to do like bases. This is 4a squared. This is just a. So if I multiply by 4a, I'll get a common 4a squared, but I need to do it on the top and bottom. Once we actually carry out that subtraction, then it just looks like a difference in the numerators over the common 4a squared. Now we can apply the square root property nicely to this one single fraction, okay? So if we have something squared is equal to something else, then that something is equal to plus and minus the square root of the something else. Now, it's a fraction, a nice fraction now, so we could distribute our square. If we distribute the square root, if you distribute the square root, what you get is, well, this bottom part is a square. This is 2a squared is 4a squared. So I could actually take its square root, and we get 2a. Hey, that just happens to be a common term with this 2a that we have over here. So if I subtract this to the other side, it's actually pretty easy to combine it over the same base. And behold, we have negative b plus and minus the square root of b squared minus 4ac over 2a. And so all you have to do to get the quadratic equation is apply completing the square to the general polynomial ax squared plus bx plus c. Pretty neat, right? All right, that's it for this video. Thank you very much for your patience and have a great day. Good luck with your studies. I'll see you in the next one.